So, schönen guten Tag. Welcome to Nonlinear Optics. I'm glad that still a few can be present. I just looked at the Goethe Gallery. So there's this Corona test station, and the queue is, well, tens of meters long. I think the people wait there for hours until they get their test. I guess it's a good idea to have a vaccination. Well, yeah, so what did we do last time? We had the coupled wave equations, right? The coupled wave equations. And actually, this is a good idea just to start this lecture with a small quiz. So the first one is, as usual, this stupid slide, whether my thing here works today, whether Poll Everywhere works. So let me check it on my iPhone. It doesn't seem to work. Does it work? Yeah? Ah, yeah, so now it works also here. Okay, now the real question, namely the coupled wave equations. What is right? So please look at these. So it's not active yet because, well, I just had to copy and paste this page because it doesn't like these equations. Strangely enough, yeah. So Poll Everywhere doesn't like the coupled wave equations, not even the right one. So I promise that one of them is right. So please check out. So I leave it here for another, well, 15 seconds or so, and then you should have made your choice. Well, there are actually 5 choices. So, but I already said that. That one of A to D is right. Yeah, got it? So then we go to the real one. Now I forgot which one was the right one. But I can switch back to it. So A got one answer. B got another answer, okay. Well, but now B is no longer sure. C also, yeah. So the only that's missing is now D. Nobody likes D. Okay, so this seems to be the result. Everybody voted? Okay, now let me, oh, D also got now. So, but most favor A. Well, unfortunately, A is not right. So, the only difference between A and B, well, let's first discuss C and D. Yeah, so we have here the second derivative, which is, of course, nonsense. Yeah? But now most choose A. Well, and the only difference between A and B is that there is a minus sign here. Oh, well, actually, I wanted to make it more stupid, A. Yeah, okay, so this is difficult. Yeah, so I wanted to leave out actually the imaginary unit. And so this is actually what I had in mind, and I was surprised that so many choose A. But of course, you are more you're cleverer than I thought. Well, I thought that you are clever, but don't laugh. But I was just surprised that so many choose A when I still had in mind that I left out here the imaginary unit, but I didn't. So this was so I spoiled it myself. Okay, good. Anyway, so it is clear what was right. Yeah, good. So this is something that comes later. Well, the other important point in this lecture was, besides the coupled wave equations, We used it for a few cases. Well, the headline of this of this lecture today will be non-trivial solutions of the coupled wave equations, which implies that what we did before was trivial. Well, really not. This is really not true, because there were two things that we were considering in particular. One thing was the Manley-Rowe relations, and of course, in hindsight, you can say this is trivial. But the thing that is certainly not trivial is the story about phase matching. Yeah, we first did a real trivial thing where we said we have perfect phase matching, and we saw that that if we assume that that A3, so the sum frequency is weak, then its amplitude would increase linearly. But when we included phase matching, then we saw a very characteristic behavior that's very important in nonlinear optics, namely the sink-like behavior of the intensity if you go away from perfect phase matching. Yeah? And we'll come to that later in a little bit more detail. So I announced the headline for today already. It's called Non-Trivial Solutions of the Coupled Wave Equation, but it won't be much more difficult, if at all, than what we did in the last lecture. So chapter 4, non-trivial solutions of the coupled wave equations. So, and what we do here in particular is the so-called undepleted pump approximation, and this is what I want to introduce first. Probably you already have an idea what it could mean. So 4.1, the undepleted pump approximation. And actually we won't do more than the undepleted pump approximation in this chapter. Approximation. Yeah. And what we did so far was actually that we assumed that all input fields, so amplitude A1 or frequency omega 1 and frequency omega 2 are kind of undepleted. So what we neglected was that photons of omega 3 and photons of omega 1 and omega 2 are destroyed. Right? So this is what we neglected. In this sense, these fields are undepleted. Yeah? And now we're obviously doing something different. Namely, we allow that at least one of these fields gets depleted. The general case would, of course, be that both fields can be depleted, which is actually what we kind of used for the Manley-Rowe relations without really, there we just looked at the intensities, right? It was clear, at least in hindsight, what comes out. So let's write that down. So far, we neglected that photons in the input fields and I just call them a little bit sloppy omega 1 and omega 2. Right? In the input fields omega 1 and omega 2 will be destroyed if one photon, if or more generally, if photons h bar omega 3 are created. Yeah? And this means both omega 1 and omega 2 were considered to be undepleted. Both omega 1 and omega 2 were considered to be undepleted. So now we have the reference to the headline. Yeah? Now it is possible actually to solve this system of three coupled equations, differential equations, to solve them analytically. And there are special functions that are doing that. These are the Jacobi elliptic functions. I guess none of you have encountered them so far, nor did I work with them. Actually, I have to say. Yeah. So, but they are very well studied functions. So in principle, it's possible. But of course, we want to. Yeah. So if things get mathematically too difficult, it's difficult to get some physical insight, and therefore we look at the situation where just one of the fields is considered to be undepleted. Yeah? And what we have in mind is the following, that we have a crystal, or let's first describe the problem. So say you want to detect a weak infrared field, and we discussed this situation already when we discussed some frequency generation, which we also discuss here. So consider you want to detect a weak field of infrared photons. Now you know that infrared detectors are kind of, well, difficult to produce because the band gap of semiconductors usually is, well, what it is. And therefore these infrared cameras tend to be expensive. In particular, they tend not to be very sensitive, at least not on the single photon level. So if you want to count single photons, maybe because they are so rare, or maybe because you are interested in some quantum phenomena, then it is a good idea to kind of, well, amplify their energy. Yeah, so amplify their energy. So to create a visible photon, say, from an infrared photon. And with some frequency generation, you can do that. Yeah? So you can just mix it with another field, and in order to make the conversion efficiency high, you would use a strong other field. Right? So say omega 1 is your infrared field, then you would use for omega 2 a really strong field in order to have a good conversion efficiency of this omega 1 photon in an omega 3 photon. Yeah? So let's take a few notes on that. We will assume that A2 is strong, yeah? And A1 relatively weak. And this means if 1 omega 3 equals omega 1 plus omega 2 is produced, then A2 hardly gets weaker. Yeah? So if we have so many photons and just take a few, then this does hardly, then A2 is hardly affected. Is hardly, well, let's say depleted. Yeah, and the application detecting infrared photons is, well, difficult. Let's just write. Yeah, I discussed what I mean. Is difficult. Therefore, converted to visible or even UV, where detectors with an efficiency, a quantum efficiency close to 1, are easily available. Okay, so if this is the case, so if A2 is undepleted, then in mathematical language this means that the amplitude does not change with propagation through the crystal. In other words, it is independent of propagation distance z. Yeah? So undepleted means that dA2 over dz is equal to 0, and then of course our coupled wave equations are simpler than they were in the general case. So we have the derivative of A1, and this is, I introduce now a few abbreviations, a few constants. So K1 times A3 times e to the minus I delta k times z, with K1 is defined as the imaginary unit times 2 times the effective nonlinearity times omega 1 squared divided by K1 c squared and then A2 star, complex conjugated. The same thing for A3, or the analogous thing for A3. So there we have K3 times A1 e to the plus I delta k times z, with K3 equals imaginary unit times 2 times the effective nonlinearity omega 3 squared K3 c squared and A2. So these are the equations 1 and 2 with which we will work throughout this chapter. Okay, so we have now a system of 2 coupled equations, and of course we want to solve them. And as you can imagine, it's particularly simple if we do this for perfect phase matching, for delta k equal to 0. And this we'll do. Actually, this special case is not so special, because what you would try to do probably is that you arrange things such that you have good phase matching, if not perfect phase matching. Yeah. So it's, and we'll see this in towards the end of this lecture, that having good phase matching is a good idea. So 4.2, some frequency generation for perfect phase matching. Which means delta k equal to 0. And this makes these equations, of course, again a little bit simpler, and its solution actually much simpler. So, and we start right away by, so we want to eliminate, say, A1 or A3 from these equations. And we do this by taking the derivative of this equation here, of the equation 1, right? And if we take the derivative, then we have, of course, here the second derivative, which is not the point. But what we also have would be the first derivative of A3. And, of course, we also have the first derivative of A3. And so we can plug in one equation into the other. So this is the idea here. So we take the derivative of equation 1. Yeah? And of course for delta k equal to 0. And if we do that, then we have, of course, the second derivative of A1. And that's equal to K1 times the derivative of A3. Now, so the next step would be we use equation 2 to eliminate dA3 over dz, so the derivative of A3 in equation 3. So this is, of course, here equation 3. And we get, of course, a second order differential equation. So second derivative of A1 is equal to K1 times K3 times A1. And we define this here as minus kappa squared A1. Yeah? So why do I write minus kappa squared? Does anybody have an idea? So if you look at this differential equation, you see, of course, that's the differential equation of a sine or a cosine, provided kappa squared is positive, right? And it's not, so it's not straightforward to say that kappa squared is positive because you see K1 and K3, which make up kappa squared, they are complex numbers. Yeah, so we better check out whether this is really positive kappa. Yeah? So this is what I want to do next. Yeah, so what is the sign of kappa squared? Yeah, so it's defined as minus K1 times K3, and therefore it's equal to plus 4 times the effective nonlinearity squared, omega 1 squared, omega 3 squared. Yeah, all of that is, of course, positive, so this is not the point here. The point is here that we have the magnitude squared. Well, we see it actually immediately at equations 1 and 2. We have A2 star times A2. So therefore, we have here the magnitude squared of A2, which means that kappa squared is larger than 0 is positive. So, and therefore, the solution of this differential equation 4 is a sinus-like function. In general, it's the linear combination of a sinus and a cosine. And this is what we want to write down. Yeah, so the general solution of equation 4 is A2 of z is equal to some integration constant b times the cosine of kappa times z plus c times the sinus of kappa times z. Yeah? And when we know A1 of z, then we also know A3. Yeah? And so from this we get, via equation 3, that A3 of z is equal to 1 over K1. Then the derivative of dA of A1 with respect to z. And if we do that, then we get minus b times kappa divided by K1 times the sinus of kappa times z plus c times kappa divided by K1 times the cosine of kappa z. That's equation 6. Well, we have two integration constants, b and z, and we use, as usual, the boundary conditions in order to determine them. And the natural boundary conditions are, of course, that there is no some frequency generation at the input of the crystal. Yeah? Of course, you could also mix, well, 3 colors. You could also start with the sum frequency, so if you have it available. And I don't know for what purpose, but anyway, yeah. So in principle, it would be possible. So use boundary conditions. To determine B and Z. Yeah. And the assumption is no omega-3 field, no sum frequency at the entrance phase of the crystal. At Z equal to 0, which is the entrance phase of the crystal. Yeah. This means that A3 of Z equals to 0 is assumed to be 0. And now if you look at this equation 6, then we find that C must be equal to 0. Right? Otherwise, we would not have 0 for A3. So this means C is equal to 0. And then if we use this in equation 5, then we can immediately say what A1 at position Z equal to 0 is, namely B. Yeah, so what we get is that B is equal to A1 of Z equal at the position 0. And then we can, of course, also write down what A1 as a function of Z is. It is A1 of 0 times the cosine of kappa times Z. And in the same way, A3 of Z, this is equal to minus A1 at position 0 times kappa divided by K1 and the sinus of kappa times Z. Okay, so we see that this kappa has an important, plays an important role, and therefore we want to see what it is. Yeah, so it's the product of K1 and K3, and K1 and K3. This is also kind of a complicated expression. We just want to calculate it by substituting the definitions into it. So compute kappa divided by K1. Yeah, not kappa itself, but kappa divided by K1. What do we have here? Okay, so we have here kappa divided, divided by K1. So we have 2 times the effective nonlinearity times omega 1 times omega 3 divided by the square root. I have the feeling I could have made this quicker. Doing here something stupid, I'm afraid, but nevertheless. So what we get, so let me write the result just. So we have n1 times omega 3 divided by n3 divided by omega 1, and then a2, the magnitude of a2 divided by a2 star, right? Okay, so what is a2, the magnitude of a2 divided by a2 star? So let's do that. Yeah? So compute a2 magnitude divided by a2 star. And what you find is that the magnitude of a2 divided by a2 star is just the phase of this field. Well, yeah, so this is what you probably would have expected. Yeah, so we expand with a2. Then, of course, we have the magnitude squared in the denominator. And this is, by definition, the phase of this field. Yeah, so what we can say is that the only role that's played by A2, yeah, so it's kind of interesting. A2 is the strongest field in this game here, right? So it's kind of the elephant in the room, but it doesn't show up in any of these equations. Also, it's the by far largest field. Yeah, so the field omega 3 can't have more photons than the field of omega 1 at the entrance phase. And because 1 photon of A1 is destroyed if I create one in omega 3. Right, so this means neither omega 1 and omega 3 can be strong. So the only strong field is A2, but nevertheless, it does not show really up. Yeah, so it only shows up with its phase. So this is kind of interesting. So phi 2 is the phase of field, again, this sloppy way to say it, of field omega 2. Yeah, and providing this phase is the only thing that A2 provides, or A2 does, yeah, besides delivering a few photons. Okay, so now we use these two expressions here, so 9 and 10, in order to write down the more or less final result. So we substitute 9 and 10 in equation 8. Yeah, so in equation, so A3 in this equation 8. And this is then 7. So 9 and 10 in equation 8. Yeah, and we see that A3 of Z is equal to imaginary unit times n1 times omega 3 divided by n3 and omega 1. Then we have A1 at position Z equal to 0, sinus of kappa times Z times e to the I, and now this phase, right? Well, if we compute the intensity, then of course the phase will be gone. So we have A3 of Z magnitude squared, yeah, so which is equal to A3 times A3 star. And this is proportional to A1 at position Z equal to 0 squared times the sine squared of kappa times Z. Yeah? Okay, so we see that the intensity, the some frequency, oscillates with in a sine squared behavior. All right, which implies that also I1, so the intensity of the amplitude 1, will oscillate pretty much in the same way, just as a cosine squared. Right? Because for each photon that I generate in omega 3, I lose one in omega 1. So if we look at it, it should look like the following. Yeah. Another question is, did you see this before? Did you see this behavior in some lecture, in some different lecture before? So, and this is actually my second, or yeah, so where did you see this before? So this is actually the question. I hope it works. Yeah. One answer could be no. I didn't see it before. I don't remember. Could be another option. No response. Nothing. So, one hint. Did you have, who had a course in quantum optics? Bloch sphere? You know about Bloch sphere? Does this help? No? Well, these are the Ravi oscillations. Yeah, it's the same equation than the Ravi oscillations. So here we have Isidor Ravi, yeah, and he's famous for studying two-level systems, initially with microwaves, right? And if you shine in here in resonance, then the population from the ground state is transferred to the excited state. So it's pumped up here, but once it's over there, it will be pumped down again. Yeah? And the more photons you use, so the higher the intensity of these photons, the quicker it will go. Right? So these are the so-called Ravi oscillations. one of the fundamental phenomena in resonance fluorescence. And this phenomenon is very important because it is one of the fundamental phenomena also for magnetic resonance, also magnetic resonance tomography, but MRI. So, and they have all kinds of tricks in order to deal with complications that can happen here, namely that if you have many atoms or molecules, right? So in MRI, it's of course done with the nuclear momenta. So they can, if you have an ensemble, then all these excitations they can dephase, and in order to get a good response, one needs to rephase it. So there are all kinds of tricks connected to that. And you probably have discussed this at some point with the Bloch sphere, right? So there's this Bloch sphere, and if the atom or the ensemble of atoms is, or nuclear, depending on what you are studying, then the Bloch vector points to the south pole. And now you can excite it such that it points to the north pole, then all of them are excited, right? And a Ravi oscillation would be to make this rotate via the equator. Yeah? So very important thing here. So here I have actually Felix Bloch, also famous for other things. So this, after the Second World War, this kind of research was also initiated, perhaps, or actually encouraged or supported by the advance of high frequency technology that was also developed for radar. And radar, of course, was important, so became important in the Second World War. So now, there's a quote by Ravi, and he once said about his colleague Edward Teller, "The world would be better without an Edward Teller." So, and because you may not know who Edward Teller was, I thought it would be kind of interesting to ask the question, for what is Edward Teller famous or infamous? For a theorem in nuclear physics, for developing the uranium bomb, the plutonium bomb, the hydrogen bomb, or satellite-based defense against ballistic missiles? So, who knows the name Edward Teller actually? I asked this question because so if you would have asked somebody 30 years ago, when I was a student like you, then probably most students would have known it, because he was also kind of a political figure. He is actually famous for a theorem in molecular physics, that's true. Right? So there is the Jahn-Teller effect. He took part in developing the uranium bomb, but he was actually not a leading figure at that time. He was, I would say, just too young. The same for the plutonium bomb, but he was the one who really pushed for the hydrogen bomb immediately after the Second World War, and made enemies already at that point with colleagues. by well, promising too much. Yeah, so the hydrogen bomb, the development of the hydrogen bomb was more complicated than initially suggested by Teller. But later he came up with the proposal that worked. All right, so he's Sakharov, the Russian Peace Nobel Prize winner. He was the father of the Soviet hydrogen bomb. He didn't get the Peace Nobel Prize for developing the hydrogen bomb, of course, but for his work thereafter. Yeah? But Teller was a different figure than Sakharov. He testified in the McCarthy area, where the Americans supposed communists everywhere. He testified against Oppenheimer, and Oppenheimer lost his clearance afterwards, and did a lot of controversial things. So why was Edward Teller famous when I was young? Because the hydrogen bomb was a historic thing already when I was a student. So 30 years old, another 30 years older. What was in the debate at 30 years ago, this was Ronald Reagan's era, this was the Strategic Defense Initiative. So what the US wanted to realize at that time was a satellite-based defense against ballistic missiles. And Edward Teller was a big supporter of that. And, again, he promised too much. And in particular, he didn't have a good idea on how to put it in reality as he had for the hydrogen bomb. And and the reason may be that it's not really possible. So he was also a controversial figure at that time. And if you read about him, then you can well understand why Ravi said the world would be better without Edward Teller, which is a pretty strong statement to a world-famous colleague. He was a great physicist, Teller, so there's no question about that. But Ravi actually also made a few other nice quotes. So when the muon was discovered, he said, "Who ordered that?" So because this came as a surprise, and people at that time thought that they understand it pretty well, and then the muon came. Who ordered that? Okay, so we did. We should discuss this curve here a little bit. Yeah, so for the Ravi oscillations, it is possible to actually get the entire population from the ground state to the excited state. Yeah, so if we can neglect spontaneous emission and stuff like that, right? And here we have a similar thing. Namely, what we can do is to convert all the photons in omega in omega 1, yeah, so in amplitude A1, which you can assume that this is this infrared field, and you can actually convert all of them into, say, visible photons that you can easily detect. Yeah, so you just need to make it right. Yeah, so you just need to choose kappa you just need to combine all the constants that we have here, namely the amplitude of A2, the effective nonlinearity, the frequencies, and so on. You need to adjust basically the intensity of the strong field, just that given a certain length of your crystal, that you come to this point. right? So you would make your crystal just this length here and choose the appropriate amplitude for the omega-2 field, and then you really can convert each and every photon, infrared photon, into, say, a visible or even a UV photon. Interesting, isn't it? Okay, now let's see what comes out for some frequency generation in the undepleted pump approximation as so far, but now where phase matching is not perfect. So this would be 4.3, some frequency generation for non-perfect phase matching. Well, if you would know resonance fluorescence, and Ravi oscillations, you probably would have a good guess on what comes out. But apparently you don't, and therefore we need to do the calculation. So we still look for a solution of these two equations. Where do I have them? Yeah, here, these two equations, 1 and 2. Yeah, so these two equations, which are the coupled wave equations just in the undepleted pump approximation. So far, we said that this delta k is equal to 0, right? And therefore, this exponential is equal to 1. Now we want to drop this simplification and nevertheless find a solution. So, now the best way to find a solution is to know the solution. And we call this an Unsubs. So we make the Unsubs that A1 of Z is equal to some constant f, which is supposed to be independent of z, times the exponential of e times g, which is another constant, plus now capital G times e times minus e g z, and then e to the minus I delta k times z over 2, right? That is not easy to find this ansatz, I would say. Z times, so for A3, it would be C times E times G times Z plus D times, and the same thing with minus e to the minus I G Z and e to the plus I delta k Z over 2, right? And this we substitute into our equation 1. Yeah, so into this coupled wave equation in the undepleted pump approximation. So this is equation 15 and 16. So 15 and 16 into equation 1. And we have to use then the product rule, of course, yeah, because we have the derivative of A1. So what we get using the product rule would be E times G times F times e to the IGZ minus EG times capital G times e times minus e to the minus IGZ. And then this exponential with the phase matching or phase mismatch delta k minus and now the second half here, I over 2 times delta k times f times e to the igz plus capital G e to the I minus igz. And again, this exponential minus I times delta k divided by 2. Right? And now the right-hand side, which is shorter, k1 times c times e to the igz plus d e to the minus egz, and then e plus I delta k times z over 2. And this multiplied with e to the minus I delta k times z. Yeah? Well, and here you see why this. Yeah, so in the Unsubs, it was a little bit surprising that we have here z over 2. But now you see why we did this. Because if you look here, then you see that, that on the left-hand side, we have minus I delta k z over 2, and here we have plus. Yeah? But by multiplying it with this factor that came from equation 1, yeah, so this was the phase matching factor in equation 1, you see that we get the same thing on both sides of the equation. So what we can say is that we can drop these exponentials. Yeah, so where we had the where we have this phase matching thing. Okay, now the second thing that we can do is to realize that, of course, e to the igz and e to the minus igz, that they are linearly independent, and therefore what we have here are in fact two equations, namely those with this factor here, yeah, so e to the minus egz, which we also have here, and then we have the one with plus. Right, so we have two equations, in fact. So, and what we do is, in German we call it Koeffizientenvergleich. In English, it's equating coefficients. So, equating coefficients. So we do it for those underlined in blue. There we have f times eg minus I over 2 delta k, now delta k I want to write, is equal to k1 times c, and the same thing for those in red. There we have minus g times ig plus I over 2 times delta k is equal to k2 times d. So these are equations 18 and 19. Yeah, of course, K2 does not make any sense. K1, of course. Yep. So we can do the same thing by substituting 15 and 16 into equation 2. Yeah, so the other one of our coupled wave equations. So let's do that. 15 and 16 into equation 2. Yeah? And then the same steps, yeah? And we would get C times EG plus I over 2 times delta K is equal to K3 times F, and in addition minus D times EG minus I over 2 delta K is equal to K3 times G. That's equation 21 and 22. Yeah, so what we have are, well, 4 unknowns and 4 equations. So it looks good. Well, but nobody wants to do that actually, right? 4 equations with 4 unknowns. But fortunately, if you look at it, then you see that that they are kind of decoupled, right? So we have F and C in this equation 18, and we have it in equation 21, but we don't have it anywhere else. And the same for G and D. Yeah, so they only appear in equation 19 and 22. So what we actually have is just, well, a system of 2 equations with 2 unknowns, but we have it twice. Yeah? So this is a system of 2 equations with 2 unknowns twice. Yeah. And we take first, yeah, so use 18 and 21. And then we can write it in matrix form in the following way. E times G minus delta K over 2. Then minus K1 minus K3. And here I times G plus delta K over 2. And then F times C is equal to 0. Right? What's the next step when we have this situation? It's always the same procedure that we would do. After Koeffizientenvergleich equating coefficients. Usually we would say, in order to have non-trivial solutions, the determinant should be 0, right? So this equation, must be satisfied for all F and C which we choose to use. Now, of course, it's fulfilled if F and C would be equal to 0. This would be the trivial solution. Yeah? But it must hold for all F and C. And this is only guaranteed if the determinant is equal to 0. This is only guaranteed if the determinant is equal to 0, right? And this means that I squared times G minus delta K over 2, G plus delta K over 2, minus K1 times K3 is equal to 0. And this means that G squared is equal to minus K1 times K3 plus delta K squared divided by 4. This is equation 23. Now, if you paid attention, then do you know what chi is? No? Well, an easy way to find it out is just to go back to the previous subchapter, namely to say what happens if delta k is equal to 0, right? So we don't do anything different. We just do something more general. Yeah, so the special case should be included here. So what is chi squared for delta k equal to 0? Yeah. Yeah, so this is the more general kappa here, the chi. Yeah, and if delta k is equal to 0, it reduces to kappa actually. Yeah, so kappa was defined. Where is kappa? Yeah, so here is kappa. Was defined as minus k1 times k3. And here it is. So what you see is that this kappa actually, yeah. So we had an oscillation. Previously, and now you see that this oscillation. Yeah. So this was kind of the oscillation frequency, but now if we make this the phase matching, if we make it different from 0. Yeah, then this frequency would increase. Yeah, so it will oscillate faster. Yeah, so this we can already say. Yeah, so the oscillation that we saw in this figure will be faster for delta k not equal to 0, right? Okay, but what we also have to do is to look for the amplitude. Yeah, so far we just have the frequency of this oscillation. Well, we assume again that the sum frequency has 0 amplitude at the entrance phase of the crystal, so at z equal to 0. So where are we? Yeah, so 7. For determining the amplitudes, or rather these constants here, C, D, F, and G, we assume again that A1 of z equal to 0 is equal to F plus G, and A3, well, we don't assume this actually, plus D is equal to 0, right? So now we can write these equations 18, 19, 21, and 22 in the following way. So this means for equation 18 to 22, for equations 18 to 22. I write it in matrix form already. Yeah, so right away. So we have 0, 0, 1, 1, and here we have C, D, F, and G. All right, so this is A1 of 0, A3 of 0, and then here's 0 and 0. So we have here 1, 1, 0, 0, and here minus K1, 0, Ij minus I delta K over 2, 0, and then here 0 minus K1, 0, and here minus Ig plus I delta K over 2. Yeah? Well, and this has to be solved. Yeah, fortunately, nowadays we have things like Mathematica, and this is, and I ask Mathematica to do it for me, and what we get is this one here. Yeah? Okay, well, with this we can actually find an expression for A1 and A3. Yeah, and of course it makes some work. Yeah, so one has to do some simple calculations. So substitute into the ansatz 15 and 16, and do some calculations. A little bit lengthy but not complicated. And then you get A1 of Z is equal to A1 at position 0 times the cosine of G times Z plus, now complicated expression, K1 over G A3 of 0 plus I delta K divided by 2 times G times A1 of 0 times the sinus of G times Z times, and now the this phase matching factor delta K over times Z over 2. Yeah? And similar for A3. There we have A3 of 0 times the cosine of G times Z plus I delta K divided by 2 times G A3 of 0 minus K3 divided by G A1 of 0 times the sinus of G times Z, and then e to the plus I delta K Z over 2. Right? And the next thing would, of course, be to calculate the intensity by taking the square, basically. So we use the special case. The special case A3 of Z equal to 0 is 0. And then we get A3 of Z is equal to K1 divided by G, A1 of 0 times the sinus of G times Z, e to the plus I delta K Z over 2. Right? And for the intensity, this means that we have the amplitude squared of A3 squared and amplitude squared of A3, and then K3 squared divided by G squared times the sinus squared of G times Z. Yeah? So, and here the interesting point is, so we already saw that that it will oscillate faster because G is basically equal to kappa plus the phase mismatch, right? But now we see that also the amplitude is affected. The amplitude goes down here, right? And actually on the view graph that I have shown and that we can look at once again, you see this, right? So this is for the Ravi oscillations, but also for the Ravi oscillations, right? You can of course detune it here. Yeah, so if you don't shine in with exactly the resonance frequency, but with a slightly different frequency, then you don't achieve a complete transfer of the population to the upper state, but only a partial one, right? And the bigger the detuning is, yeah, the quicker this exchange of population takes place, but the more incomplete it is. Right? And we have the same behavior here for for some frequency generation in the undepleted pulp approximation. Yeah, that's it for today. We're a little bit faster today by design actually, because we were did a little bit more last time. And also because I don't want to spend 15 minutes on just starting a new chapter. The next chapter, guess what it will be? No, we will actually look at second harmonic generation. Now, we don't want to solve the Jacobi elliptic equations. I would have to give and prepare actually a few mass lectures on elliptic functions. I don't want to do that. And actually it would not pay off in the sense that of course we want to find constellations that are relevant for applications. May these be applications in science or applications in technology. Yeah, so we will look at the coupled wave equations for some frequency generation. So we will derive the coupled wave equations, not for some frequency, for second harmonic generation, and we want to solve them. Yeah? And it will be a lot of stuff to write, and I won't do that. I will just show it and explain it on slides. Yeah, so then see you next Monday. Have a good week.